All right, good afternoon, everybody. So we had a very illuminating set of discussions in the Building a Better Ruler section. I modified it a bit here to be building and using a better ruler because about half the talks were about cool things that you can do with the calibration sources that we've got now. And I have a punch list here of some neat results presented by each one of our speakers. And any further questions you have about any of this stuff, I would direct you to them. And of course, I can't hit on all of the interesting things that were brought up in our session either. So you can take a look at the recording of it later on if you're interested. So thinking about building and using a better ruler. Building, first of all, we heard about an exciting set of things that the group at NIST is doing from Pooja Sekar. She discussed new broadening methods in particular that they're looking at, which are shown here in the plot, particular using some Piplin devices to get laser comb light that extends really far into the blue, which is an issue that we've all been interested in tackling, as well as some new architectures for different types of comb generation using electro-optic techniques. So exciting techniques being pushed on there. We heard from Menlo Systems and Jason Reeves as well. He pointed out some new things that they're working on for their Astro combs, addressing robustness and things like that, as well as some new hardware mechanisms that they're looking at, in particular, some potentially exciting results with new broadening fibers and work they're doing on that. So he pointed at a paper with the title that's pasted here that I guess we should be excited to look for. As well as some new micro-resonator-based architectures that they're looking at as well. So new exciting comb architectures being developed in a number of different places. And Nem Jovanovic made the point that just making the comb isn't enough. You want to get it flat as well. And so he showed a really exciting system based on arrayed waveguide based. Well, it's an AWG-based flattener, which is as effective as and quite a bit cheaper than some of the other methods that you might use. And so he showed results like they're shown here of a flattened comb, sort of using one of the early versions of these systems. So some exciting techniques for making the comb flat, which is important to actually make use of it as well. So those are some of the things that we heard about in terms of hardware development. And then switching over to the using the ruler kind of talks. We heard some interesting things from Christoph Lovis about how they're actually able to use not a comb, but the thorium argon lamps and Fabry-Perot etalons, and looking at those spectra very carefully, thinking about them carefully to get very, very good wavelength calibration on espresso data. So you can see the residuals to their cavity fit, which sort of embody the quality of the wavelength calibration shown in the plot here. Xavier Dumusc made the point that if you differentiate the wavelength solution from the drift, you can profit quite well because although the spectrograph wavelength solutions that we have might be fairly complicated and not necessarily smooth, we have generally paid a lot of attention to making the spectrographs quite stable. And so the drift is generally easier to parameterize. And he showed some exciting results improving the stability of the wavelength solution by looking at things that way. Gaspar showed some results using either one or two LFCs to characterize the drift on espresso and harps, and all kinds of interesting things that you're able to do with characterizing the line shapes, for example. And what's shown here might be a little hard to see, but the clear signature of CTI or CTE in those measurements that are enabled by the comb there. And some interesting stability results and things like that too. Lily Zhao made the point that if you've put all this energy into building these fantastic calibration sources and laser frequency combs give you all this information, you should probably trust them to tell you what they're capable of telling you and use the information that's there to learn how your spectrograph is drifting. And she presented a software package called Excalibur, which is a non-parametric hierarchical technique to parameterize and figure out how the spectrographs are actually drifting and what their wavelength solution should look like, and then to get the wavelength solution from there. And finally, thinking even further outside of the box, I suppose, there's some exciting ways to use the stellar spectra as rulers themselves in a way. And so Michael Crédigné presented some exciting results using the line-by-line information from stellar spectra and looking carefully at the results from those data sets over time. And he showed the ability to recover some exciting systematics in his data sets there. And so all kinds of different ways that folks are pushing on developing new types of rulers and using those rulers in creative ways. So again, if you're interested in talking any more about any of those things, I would encourage you to go talk to any of those speakers that I just mentioned. So I think those are the wrap-up points from the Building a Better Ruler session. Should I switch it?
Well, you have the hit list. If you have any questions about those things, you can check out these slides. And we'll hear about Zoe next about the machine learning Splinter session. And then, okay. Thank you.
Okay. Yeah, so we, in the machine learning Splinter session, heard from some really great speakers. We started off with kind of an introduction to machine learning methods, common misconceptions, things like this. And then we had a really great talk from Sarah Blunt talking about other metrics of evaluating your models beyond just using BIC, but using things like AIC, WAIC, other stuff like this. If you want to know more what that exactly means, I would look at the recording that Sarah, from the talk that Sarah gave. And then we also had a really great talk about kind of the history of Gaussian processes from Belinda Nicholson, giving kind of an overview of what the group from Susanna Gray at Oxford has been working on. And then after that, we had a really lively, long discussion, kind of talking about a lot of different things, which I'll kind of focus on in the report out. So first, we kind of talked a lot about which statistical or machine learning methods are most promising for EPRV science. Our panelists discussed modeling stellar variability in the full spectrum and how that will require a lot more complex models to be able to do this. We also discussed the possibility of using transfer learning, where you pre-train a neural network, maybe on some set of stars that span various types of stellar activity, and then get this to work well on out-of-sample stars with methods like recurrent neural networks, for example. We also discussed how we really want to make sure that all of these methods are explainable and ideally also physically motivated. One of the ideas discussed was also to create more physically motivated kernels for Gaussian processes by collaborating more with mathematicians and statisticians in the departments often neighboring our departments. We also discussed extensively kind of some of the concerns and pitfalls that people have with these methods, especially because, yes, they're very powerful, but they're also a lot more flexible, so we have to be really careful. So some panelists discussed that it's dangerous when people are kind of blindly applying these methods without fully understanding them. So again, interpretability and explainability is really critical. Some panelists also noted that some of the aims or goals of industry professionals who are making these kinds of machine learning methods are kind of distinct from our goals as scientists. A lot of the time they want to produce new data, but they're not necessarily interested in maybe some of the underlying physics or the underlying kind of mechanisms that are producing that data, whereas we really do want to make sure that we understand those things. And so that just means that we kind of have to consider that when working with them, but at the same time, that doesn't mean that collaborating with them can't be very fruitful and very useful. Talking about industry, we also discussed how it would be really great if the field could do kind of more sharing across people who are in industry versus people who are in academia and having more kind of back and forth between the two, rather than seeing someone who's going into industry as having completely left the field, but instead maybe seeing if they would still be interested in collaborating with us. Some panelists also discussed that they had experiences doing internships in industry and how this actually gave them a lot of new ideas for their own science. And then we also had a whole discussion about how can we make these methods more accessible? How can we make sure that these are more easily understood, but then at the same time, not sacrificing kind of the complexity of the math or the understanding of these methods. I think a lot of the panelists were really optimistic that the astronomy curriculum is kind of evolving to include more statistical or machine learning methods or software engineering in the curriculum. And at the same time, it would be helpful to kind of invest more financial resources into these kinds of things as well, and in the education of these methods so that they can become more accessible. Yeah, I think one suggestion that I thought was kind of funny that people just said that we should just throw more money at people making cool plots or cool diagrams that help us explain these kinds of methods. And helping people also build more intuition. So it doesn't always have to be a very, it could be a textbook sometimes, but it could also be like building the packages that people are so people can play around with GPs or machine learning methods and learn more through intuition as well. I think overall we had a really productive session, really great discussions. And on Thursday, we'll be focusing a little bit more on deep learning methods as well. So we're really looking forward to seeing people at the Thursday Splinter session as well. I forgot about questions.
Are there any questions about machine learning? It's kind of hard to believe. Great. Well, if people are interested, they can stay tuned for the Thursday session. Let's thank Zoe again.
Hello, everybody. So we had a very interesting and lively session about the near infrared radial velocity spectrometer with a very nice comparison between different instruments. So first we learned the lessons from Carmenes. So on the left diagram, you have the RV photon noise in different wavelengths. So one point was that, for example, if you have a star around 3,200 Kelvin, the best spot is around 700 nanometer. So it means that a visible instrument is even better than a near infrared one. Obviously, if you go down to lower temperature, then near infrared makes sense. The fact that they limit their exposure time by the signal to noise ratio in the optical makes that the photon noise in the near infrared is worse than in the visible. So this is the kind of median photon noise that they get, 1.6 meter per second in the visible and 6.2 in the near infrared. Then from HPF, we learned about drift models. So at the beginning, you follow the drift in RV just by simple pixel shift, simple offset. But after a few years, you need higher order terms. So you do linear scaling of pixel scale, and they are now using 3-parameter model. And also they are using the laser frequency comb to define the line spread function. And they see, for example, in a single order that there is a variation of the LSF with the wavelengths. So this is something that it has to be taken into account. Then from Spirou and NURBS, we learned that having 2 instruments and 2 pipeline, and one of the pipeline being used for both instruments is very useful because you can disentangle the instrumental effects from the DRS effects. They talked about modal noise, telluric correction, and a lot of things with the infrared detectors, which makes a real mess. So CCDs are easy stuff. The NIRPS modal noise, so they have 2 modes, the high accuracy and the high efficiency. And so the modal noise out of the box is quite large, 6% for example, the high accuracy. But then they have different things that improve. And at the end, you reach a level which is below 0.5% in both modes. And there is a comparison of what Etienne Artigot presented as the trumpet for the LBL RV measurements between NIRPS, which is the top diagram, and Spirou, which is below. So you can see, for example, that in the Y band, which is on the left, NIRPS is outperforming Spirou very clearly. But in Spirou, we have the K band. And the reason why we are quite bad with Spirou in the Y band is because we have these rhombs that are used for the polarimetry and that do not have a very good transmission in the blue. So you cannot have everything on a single instrument. Then from IRD on Subaru, they give some median RMS, so about 2.5 meters per second on their sample. And there is a significant contribution from the fact that the modeling of the tellurics is not perfect, about 1 meter per second. They also insisted about the LFC brightness stability, because when you have change in flux, you have change in the radial velocity. And they also talked about the activity indicators to disentangle planet detection from activity signals. And also something which is maybe unexpected is that for this near infrared instrument, going to later M dwarfs does not mean that you are improving your performance, because they are using adaptive optics, and the performance of the adaptive optics is worse for cooler stars. So they plan to improve that with an infrared wavefront sensor. So the discussion then was about what are the fundamental limitations of near infrared RVs. So we talked about detector issues, tellurics, pipeline complexity, photon noise, and also one thing which is very important with the H4RG detectors, that is persistent. So when you observe a bright star and then you observe a faint star, you have a shadow of the spectrum of the bright star on the next spectrum, which is quite difficult, and you have to wait a long time for this to disappear. Then we discussed what is important to do in the near infrared. So obviously it is to learn about the stellar activity and to improve the robustness of the planet detection. We discussed about the adaptive optics on the near infrared instrument with several things that are listed here. The complementarity between the optical and the near infrared. So how to do a proper weighting between, for example, the activity signal, which is changing with the wavelengths, and the accuracy of the instrument, which can be better in the optical. The idea of organizing a data challenge between these different instruments and different pipelines, and a list of points that are listed here that we didn't have time to discuss. Thank you very much.
Great. Are there any questions for Pascal?
So 10 years ago, with the problem of activity, a lot of people said, okay, we have to go to the near infrared because it's really the sweet spots there. But today, with all the instruments that we have, with model noise, with complexity in the detector, what is basically the current status?
What is the current
status of, is it really better, what, except if you go to M9s or L dwarfs, is it really better to go in the infrared?
As I am working in the infrared, I would say yes, but maybe you will not be convinced compared to espresso. So I think that we cannot reach the same precision that you have in the optical, but obviously every time you have an active star, I think that you really gain going to the near infrared. Not necessarily getting better data, but getting information about the activity, especially if you have a polarimeter like in Spirou, or because you really can characterize the activity, subtract the activity. I was thinking of stuff like a unique. You cannot do anything in the optical if you don't characterize the activity at the same time, so that you can detect the 3 planets that are now known around that star, that young star. So young stars, for example, is a sweet spot for the near infrared and with polarimeter.
Any other ones? Okay.
Just a comment that sometimes these conversations get cast as optical versus infrared, right? What we really need to be thinking of is optical and infrared, because sometimes these communities are separate, but there are very interesting things you can do together with the optical and infrared. I really think those are the interesting questions, perhaps.
Yeah, so for example, in France, we have a project which is called Vision. And at the TBL telescope at the Pic du Midi, we will combine a visible spectropolarimeter with a near infrared spectropolarimeter. And we have a plan to do that also at CFHT between Espadon and Spirou. So having from 380 nanometer to 2.5 micron in a single row, and with polarimetric capability.